Okay, so our problem is y equals 2x squared divided by x squared minus 9. Okay, so first we're going to find the asymptotes, or the simps. And as you can see here, there is one simp. So now we must find the rest. Okay, so to find the asymptotes, we have to set the denominator equal to 0. So if we do that, it'll be x plus 3, x minus 3. And then it'll be x equals negative 3, x equals 3. So these are the vertical asymptotes. And then to find the horizontal, we have to divide the coefficients because these are the same power. So then y would equal 2. Okay, so now we need to find the domain. And since we have the asymptotes, it's very easy to find. So negative infinity to negative 3. And then negative 3 to 3. And then 3 to infinity.
There. There's no holes.
Yeah.
Alright, so to find the intercepts, we have to plug in 0 for x and y. So if we're trying to find the y-intercept, we have to plug in 0 for x. So when we do that, it would be 9. So then it would be 0 over 9, which equals 0. And then for the y, we have to plug in 0 for y, and then set that equal to the numerator. So then this would just equal 0 also. So then it would be 0, 0.
Go.
Alright, so to find the symmetry, we have to plug in f of negative x. And, like see what it's like compared to f of x. So let's do that real quick. So I'm going to plug in f of 1. And when I do that with the original equation, let me just do this out real quick. So this is going to equal negative 1/4. And then if we plug in f of negative 1, you'll see here. It's going to equal the same thing. So what does that mean? It means that it is even. This is pretty cool.
Pretty cool.
Pretty cool.
Fine, and behavior we have to see limits. So limit of f of x as x approaches infinity. This is going to be 3 because of the vertical asymptote. So then we have to do lim of f of x as x approaches negative infinity. And then this is going to be negative 3 also because of the vertical asymptote. Pretty solid.
Yes. So we're finding local mins and maxes, right? What we did here is we took the first derivative, and when you do that, you get 4x cubed minus 36x minus 4x cubed. So the 4x cubed square, obviously, or cancel out, and what you want to do is you want to set the top equal to 0 to find your local max. When you do that, you get 0, 0. So our local max is the only one that says 0, 0, it's the origin. Alright, so let's go time to find some intervals. So what you want to do to find intervals, right, is you want to basically, so what we know right now, right, we know that there is 2 asymptotes. One at x equals 3, one at x equals negative 3. So we know that there's going to be 3 sets of intervals. Because we know there's no holes, there's just these 2 discontinuous points. So it's going to be like negative infinity to this point, and that's going to be like something in between. But now let's figure out, where in those intervals is it positive or negative, right? And positive, negative as in concavity. That's what I'm talking about, So when you do that, I mean not cavity, but you know what I mean. You know what I mean. Like increasing or decreasing. So the way you do that, basically, is you have the derivative, right? We did that before. You said how the derivative was 3x or 36x over x squared minus 9 squared, right? So that's derivative. So why don't we just plug in a point that is past negative 3 to the left, and if it's positive, that means it's going to be increasing that entire way. And then we know that there's a local max in between these points. So we know that's at 0, 0, right? It's a 0, 0. It's local max. So we know with local max it's going to decrease on either side of that. Okay? So we already know that off the bat. We know that that's going to be, we'll fill this in over here. We know it's going to be, we'll do increasing off the bat, we're gonna leave a little space here because we know we want to plug in later. But we know off the bat, right? -3 to 0 is gonna be increasing. But there's gonna be another thing right here that we have to find out. And the way we find out what's after the asymptote is you just want to plug in a point, an x value, and see what the derivative is gonna be. Because the derivative is positive, that means it's increasing the whole time because it's uniform. Right? So let's put in like -4, right? Right? And if we do that out, you'll get negative fuck, wait, no, you don't get that, that's how you get.
It is.
Alright, hey guys, Zach. So, you know what we're doing here? Find some intervals. So, what we know so far is that there's two asymptotes, one at 3, -3. I know there's a local max here. Alright? Now, the way that we're gonna do this, right, is we're gonna basically, we know already, we put this in here, -3 to 0, we know that's increasing because when you have a local max, it's decreasing on either side. So that means what's over to the left of it is gonna have to be increasing because it's going down. You know what I'm saying? You know what I'm saying? It's going like oop, bop. It has to go down on both sides. So that means the left side has to be increasing and the right side has to be decreasing. So we can also put over here, or we'll do it over here. We'll do it over here. We'll do it over here. How long is it? We'll do it over here. Right? And I left a little space here. Whatever. Because I left some space here. Because we're going to find out what the other one is. So the way we do this, we find out what's after the asymptotes, because the graph still exists after the asymptotes, is we're going to plug in an x value into our derivative equation that we have here. And we're going to see if it's not positive or negative. If it's positive, that means this it's increasing. If it's negative, it means it's decreasing. So we did it over here. This is negative. If you do this out, you'll get 1, 4, 4 over you get that over 25. So this doesn't really matter whatever that is, but because that's just the slope at that point. But we know that the slope is uniform on that side of the graph, so that means it's positive. So that means from in negative infinity to -3, it's also increasing. Sweet. Alright, and now for the last part, we're going to plug in a value that's after the positive 3 asymptote. So if we plug in 4 here, right? Let's just switch this around, right? We'll just get rid of that. Erase this. Plug this in. Probably get an eraser. You know, we could solve this out, but just by looking at it, you can see that you got 4 squared, right? 4 squared is 16. 16 minus 9. That's going to give you 5. 5 squared is 25. This is going to be a negative. So a negative or a positive, that's a negative. So this is going to be negative. It doesn't really matter what it is. You can do it out, but it's not necessary. But since we know it's negative, we know it's going to be over here and it's decreasing. So that means from 3 to infinity, it is decreasing. So those are our intervals. And, Alright, so going over the inflection point, right here we have the math. If you do it out, you get negative 108x squared equals 324. And if you take the square root of a negative, that's imaginary. So that means there's no inflection point. Got the concavity. So what we did here is we had the second derivative and we had these intervals. These intervals are from our asymptotes because since we didn't have an inflection point, we plugged in numbers that were in between these intervals. We got a positive for the first one, which means it's concave up. The math's right here, if you want to look at it. And then we got a negative for the middle one, which is concave down. And then we got a positive again, which is also concave up. Our thing graphed, what we did here is we knew that this was increasing, and we knew that the y asymptote was 2. We knew that the x was -3, so it has to look like something like that. We had over here we had the 2 x asymptotes, and we had the local max, which means it's going to be a parabola going down. And then we knew at the end it was going to decrease because of our intervals, so we just drew it like that because we have the 2 asymptotes that it follows. So yeah.